consider this simple, starter problem with a beam, right? And we have one applied force, 2 meters, where point A, is a point where the beam is attached to a fixed surface. We can imagine this such as a wall. Okay. Now the first thing we want to be careful with is this question gives us the beam mass. So in this question, we are not assuming that the beam itself is massless. In other problems, you may assume. However, in this one, we're going to have to account for the weight. So when I look at this beam, right, I want to say the mass of this beam is 100 kilograms. So we want to find the weight force, right? We want to find the force that this beam has due to gravity, right? And where that force is going to act is at the center of mass, right? Or is at the center of gravity of this beam, sorry. The center of gravity of this beam. But because this is a rectangular beam that is, we're assuming, evenly distributed with its mass all throughout the beam, it is going to act halfway between the beam. Seems pretty intuitive, right? So it's going to be at around 3 meters halfway through the beam, and this force will act downwards, right? Downwards in the direction as long with gravity. So when we calculate our force due to gravity, it will be 100 times 9.8. That'll get us 980 newtons. Okay. Next, we want to analyze our reaction forces. So whenever we have a statics problem, we always want to look, are there any reaction forces? Now, the only reaction forces we have will be the forces centered around this fixed point, A. So A, right, is going to have a reaction force. I'll use a different color, actually. Use red. A is going to have a reaction force upwards. We'll call this AY, it's a reaction force. It can also have a reaction force horizontally. We'll call this AX. Okay? And later you'll see that AX is actually equal to 0 because there are no other horizontal forces. We'll get to that later. And lastly, with any fixed point surface, right, so this beam attached to a wall, there is what's called a restorative moment, right? So this moment is basically going to counteract the bending effect that this wall wants to have, right? So as we push down on this side, it acts like a lever and tries to basically unhinge the wall or rip off the wall, right? But this moment, this restorative moment at A, is a reaction moment that is going to basically keep our beam fixed to the wall, right? Otherwise, our beam would be flying off the wall. That's not what we want. So, right, let's get to actually plugging in some numbers. So the first concept that you're going to have to learn in statics is that in any static beam problem, right, all the forces must equal to 0, or specifically the sum of the forces must equal to 0, right? And the same thing for the moments. The sum of the moments have to equal 0, and you'll see why I took the moments at point A. It's important to choose the point at which you take your moment calculations based off of. Okay, so let's get started with the Fy, the forces in the y direction. So currently we have 3 forces in the y direction. We have Ay, we have our weight force due to gravity, and we have our applied force. So let's go ahead and add these up. We're going to assume that an upwards force is positive and a downwards force is negative. So I'll go ahead and say that Ay is positive and that we have a negative 1200 Newton force applied downwards, as well as a negative 980 Newton force applied downwards. And it doesn't matter that these forces are all out of line. That'll be covered later with our moment. So our moment will cover the fact that the forces are out of line. Currently, we just care that the forces, the magnitude of the forces on each end of our beam are balanced out, right? And so if I set this equal, I can actually solve for Ay immediately, right? Because I don't have any other variables in this equation. So let's go ahead and do that. That'll be 1200 plus 980. So that'll get us 2180 newtons. So this is the magnitude of the reaction force for Ay. Okay. Now moving on to some of the forces in the x direction, our horizontal forces, right? If we look, we only have one horizontal force, right? So the sum of our horizontal forces is actually just Ax. But we know that the sum of our horizontal forces have to equal 0. And so Ax is just equal to 0. Now, if I had applied maybe a side load to this beam, an applied force of maybe 200 newtons, right, and this was my only horizontal acting force, then Ax would be equal and opposite to the magnitude of that force, right? It would counteract that 200 newtons applied force on this end. Or even, right, if you bear with me, even if we had maybe applied, instead of a straight vertical force, we had applied a force at like a 45-degree angle, right? This would now have a horizontal component of force, which we would have to account for in our AX, or our force balance in the X direction. So lucky for us, that's equal to 0. Now, here comes the tricky part. We have to analyze the moments, right? And so the moments is just a force applied at a distance from a reference point. And that reference point can be anywhere we choose on the beam. It can be the middle, it can be the ends, right? But it's wise of you, especially when the problems start to get more complex, that you pick a reference point that eliminates as many forces as you can. What does that mean, right? So when I pick my reference point to be A, notice there are two forces interacting at A. Now the horizontal forces, we don't care because that doesn't create a bending moment, right? That compresses our beam, but that doesn't necessarily bend our beam in any which direction. So really, when we're looking at our moments, we're looking at the forces that actually cause the beam to want to turn about that point, right? That would be AY. However, AY acts at the turning point, and so we actually don't need to account AY for our moment calculation. Now, it's a good thing because that reduces the number of unknown variables. If this was a more complex system, choosing a bad reference point can get you roadblocked. And so we'll build good practices now and choose our moment point to be about point A so that AY cancels out. Now we only have two forces creating a bending action, and that is this 1200 Newton force, which creates a bending action like this in the clockwise direction, and the 980 Newton force due to gravity, creating the same clockwise bending motion, right? So our our moment about A, restorative moment, has to counteract these other two moments. So let's go ahead and calculate this. We'll go ahead and say that we'll do the 1200 Newton force. So 1200 newtons, right? And let's look at the distance it acts away from point A. So the distance it acts away from point A is 2 meters. And so we're going to multiply, right, 1200 newtons times 2 meters. Okay? And now we have to check the signs. So the convention for signs, typically, at least the ones that I was taught, is going to be, right, negative is clockwise and counterclockwise is positive. So when we look at this moment, right, it causes a clockwise moment, so now we're going to have to add a negative sign in front of here. Okay, next comes the 980 Newton, and it is acting at a distance from 3 meters. So let's go ahead and do that real quick. 980 times 3 meters. Right? This is newtons. And that will all be equal to 0. Oh, sorry. I forgot. We're looking for MA. So MA will be a positive moment, so we'll go ahead and add the moment, MA, right, is equal to 0. So MA, the restorative moment, we can solve for. It'll be equal to 1200 times 2 minus 980 times 3. And that'll be a restorative moment of 540 Newton meters, right? Because we did force times a distance, or in other words, a torque, right? Better known as torque. Newton meters is the units for torque. Okay. So this is all of our restorative forces on this beam, or our reaction forces and moments on this beam. I hope you enjoyed.